for us to collaborate with the core. Thank you for collaborating with us. We are very excited. Just a quick introduction of St. Mary's Research Center. We are the research arm of St. Mary's Hospital, and our mandate is to develop and structure research across 4 research domains: cancer care, primary care and health systems, older adult care, and surgical science. Our work focuses on high impact initiatives such as the integration of patient reported outcome measures, the use of virtual reality in older adult care, cancer prevention strategies, and innovative approaches to health communications such as social media. And in parallel, we maintain a very strong clinical trials program in oncology. We are generally excited about today's seminar, and we hope that this is just the first of many opportunities to come. Thank you.
Great. Thanks so much for that introduction. Can you hear me?
Yes.
Okay. My name is Benjamin Smith. I'm the director of the Center for Outcomes Research and Evaluation at the Research Institute of the McGill University Health Center. We're super happy to have this inaugural joint seminar where it's exactly what we're trying to do, as you described, is building bridges between the various hospital-based research institutes so that we know what other people are doing, we know what methods and domain interests there are to try to elevate the impact, the quality of the science, address important problems. So over at CORE, we are approximately 150 scientists now. So we're big and growing. We span really quantitative, qualitative methods, various disease domains, usually related to clinical care or, prevention, treatment, outcomes, etc. So it's great. So I don't want to steal too much time from our speaker today, Professor Erica Moodie. So she is a biostatistician here at McGill, main campus, Department of Biostats and Occupational Health. She comes here by way of Oxford, University of Washington, and then here, more or less. She's a Canada Research Chair, Tier 1, in the precision health space. She's had many prestigious roles, presidents of societies, co-editors of journals. She taught me Biostats 101, circa 2010. I remember it vividly. Excellent. And I'll stop there and let her tell us about heterogeneity of effects.
Thank you. Okay, thank you. Oh, that's okay. Excuse me. Thank you very much for inviting me. I'm happy to be here in the room with people I know and work with, and also at St. Mary's, because I do actually work with Sylvie Lambert and a few other people there. So it's very much a pleasure to be with you today. I am, as Ben said, a statistician. I knew I taught you. I didn't know if I should bring up the potential trauma of Epi 607, but okay. Anyhow, I am a statistician, but I know this is a mixed audience, so I've tried not to put in too much math. There may be a few footnotes of equations, but I will rely on a general knowledge of regression, so straight lines primarily, and I will allude to things like propensity scores. So we use those to model treatments as a way of dealing with covariate imbalance. It shouldn't get more technical than that. But if anything is confusing, please stop me. I'd rather stop and answer questions as we go than have anyone sort of confused or fed up or tuning out halfway through. The other thing to say again is I'm a statistician. I actually don't know a whole lot about kidneys. So if I say anything stupid, people can correct me or look the other way. So if I get anything wrong, bear with me. But hopefully it's not too far off. So the final thing to say is this is really the work of Misha, who is a PhD student of mine, jointly with Dipankar, a statistician down in West Virginia, and Dave Stevens, who is Misha's co-supervisor and also my statistician husband. All right, so I'm a big fan of this quote because I work in causal inference spheres generally. I do a lot of work with observational data where we have to worry about confounding and other sorts of biases. And a lot of causal inference deals with average treatment effects. What happens if I give everyone in the population the same treatment versus withholding it? And really looking at these sort of almost policy level decisions. And yet I think that while those can answer useful questions, and they're certainly useful for policymakers, they're maybe less relevant clinically because generally you don't think about an entire population of patients receiving only one treatment. There's lots of different treatments available, and some might be better for some patients than others. I'm not talking about this today, but I do a lot of work in depression. And in depression, there are roughly 25 different antidepressants that have been licensed for use. All of them show moderately good average effectiveness. But individual patients have very different experiences. And typically, there's a trial and error process of trying to find the right drug for the right patient, right? So we don't tend to have one treatment per diagnosis, but rather we try to find the right, you try to find the right treatment for the right patient. And Bradford Hill maybe is a name familiar to some of you. He came up with what are often called the criteria for causal inference, although he said they were not criteria, they were conditions to assess it. So he's often thought of as sort of the grandfather of causal inference in medical statistics, and yet he wasn't focused on these average effects, but rather asking about, should a fixed dose be given or should it be allowed to vary with the apparent needs of the patient? So there's been a long interest in learning about individualizing or making treatment more specific to a patient. So precision medicine broadly aims to tailor individual or treatment recommendations or treatment prescriptions to individual characteristics of the patients. And those can be sort of macro type characteristics, so age or family history, or they can be something more precise like genetics. It doesn't always help to tailor, right? If I trip on the way out of here and break my arm, I need a cast. Probably nothing more than that, and probably the same for all of you, right? So it depends on the treatment. But tailoring can improve outcomes if there's heterogeneity in how patients respond. So as I mentioned, depression treatment is a great example of that. Different patients respond in different ways. Some might find a particular treatment has intolerable side effects. Others might find that a given treatment doesn't have the right therapeutic effect. So if patients respond differently, then we might treat them differently. We might also tailor treatment over time. So if patients change in how they respond, or if their disease is changing over time. So we could think of a pain condition, for example, where patients may experience more or less pain at different times. They may grow used to the treatment they're taking and need to change the dose or change the type of drug they're taking. And we even see that how a patient responds to a given treatment gives us indications about how to treat them later. So back to my statistical world, what does this mean? Well, if we think about this in a simple regression context, for those of you online, I will be starting off with the picture at the far left of the screen first. What I'm showing you in each of these graphs is a case where I've got an outcome Y, and I'm going to assume bigger is better. So you can think of this as quality of life, for example. Along the x-axis, I have some quantitative covariate, could be a symptom score. And I'm showing you two lines. Hey, there's a solid line corresponding to treatment level 1 and a dashed line corresponding to treatment level 2. So this is just a plot or a sort of cartoon of a linear regression showing how patients respond, their quality of life score, to a given treatment as a covariate changes. So if we look at the picture on the far left, we see that there's a linear relationship between the outcome and the covariate, and that solid line is always higher. So if big Y is better, that would suggest all patients should be getting the solid line treatment. No matter where we are in the covariate space, it's always leading to a higher expected outcome. If we look in the middle graph, we have what's known as a non-qualitative interaction. So the lines are no longer parallel, but across the range of the covariate where we actually observe patients or observe this covariate value, the lines never cross. So what does that mean? Well, there's a greater benefit to having the solid line treatment if you're at the high end of that symptom score, but it's still always better to give that solid line treatment. So what we're really looking for in this precision medicine or this tailoring treatment space is what are known as qualitative interactions. So the little cartoon on the far right here. So we have an interaction, our lines aren't parallel, and they cross somewhere in the range of the covariates where I actually observe people. Right? So what I see with this crossing line is that to the sort of high level of X or the far right of my graph, treatment A equals 1 is better. That solid line is higher, but at the low levels, the dashed line is higher, which suggests that treatment level A equals 0 is better. So that's what I'm looking for as a statistician. I'm trying to find these interactions, and then really what I want to see is where those lines cross, because that's the threshold that tells me how to allocate treatment. So broadly speaking, that's what I'm trying to do. So variables that exhibit that qualitative interaction are sometimes called tailoring variables or prescriptive variables. They tell me how to prescribe treatment. So they're not necessarily, well, they're typically prognostic, but they're not just prognostic. They don't just tell me how the outcome changes, they tell me how to change my treatment. There's a ton of stats literature and indeed computer sciences literature and behavioral sciences literature on these types of treatments. In the stats literature, these are often called individualized treatment rules where we're trying to tailor to the patient. Sometimes they're called adaptive treatment strategies, dynamic treatment regimes. So if you're looking for the literature, there's a vast number of search terms, many of which don't agree, but they're all actually targeting the same thing. All right, so the context that I'm going to be talking about today is that of kidney transplant. So it's one of the most frequently transplanted organs, representing about 65% of all transplants. My data is a little bit old here, but worldwide in 2022, there were over 100,000. And in the US, and I did check, but I couldn't find great Canadian stats. It looks pretty similar in Canada. The wait time in the US is 3 to 5 years. Does that jive for Canada? A little shorter here. Excellent. Better in so many ways.
Ontario, though.
Okay. All right. Again, this is focusing on US data because that's what I was working with. Roughly 30% or just under a third of individuals who died or were taken off the waiting list had been offered a kidney and declined it. Okay. There's some sort of funny conditioning going on here, but of the organs that were eventually transplanted into someone, so an organ that found its home happily in a patient, 4 out of 5 of them were declined by at least one person. So what does that tell us? It tells us that most of these organs were probably viable because they did eventually find a home. Of the kidneys that are transplanted, again, many of which were declined, most are still working after a year. So 90% working after a year, 75% working after 5 years. So again, what does this tell us? Most kidneys were declined. Most of them are still working. So lots of kidneys that get declined were good, viable kidneys. We don't know the reasons for transplant, at least for declining the transplant in our data set, but it does raise some questions about whether patients should be declining these transplants because clearly a lot of these kidneys are good, healthy kidneys that could go on to help people. So what we wanted to do was use the methodology we have from precision medicine, which is usually used to see how to tailor a treatment, and see whether instead we could give some guidance on when to not decline a kidney. So if a kidney seems suboptimal, is it really for a given patient? The context we're working in is not so relevant anymore. Okay, the context we were working in was that of hepatitis C positive donors. So is it okay to give a kidney from a hep C positive donor to a hep C negative recipient? Why does this matter less now? Because we have fantastic treatment for hepatitis C that was not so available in the time that we were using, or in the period for which these data were collected. Okay, so recent studies and of course improved HCV treatments with these DAAs now suggest that it's really not a big deal to have these mismatched patients. But in the period of time for which we have data, it was a much bigger deal because the treatment for hepatitis C was long and far less successful. Now it's short and just really expensive, but very successful. So our question was, back in these days, could we identify subgroups who were at the least risk of a negative outcome if they were to be given a transplant from an HCV positive donor? Is this relevant clinically now? No. I still think it's an interesting methodology, interesting context that can perhaps be relevant to other questions. So we're using data from the Organ Procurement and Transplant Network database. So we have a little over 300,000 patients who were transplanted between 2001 and 2022. Those patients, about 16 of them did have a graft failure, and another 16% roughly went on to die with a still functioning kidney. So these are two bad outcomes we would certainly like to avoid. And then another feature we needed to address is that these patients are clustered within different transplant centers. So we had 251 centers. And obviously, the different centers are probably going to have similar outcomes, right? Bigger centers might have better outcomes because they have more experience, for example. Or there may simply be just very different patient mixes. So that clustering is something we also wanted to account for. Now, this idea of having multiple bad outcomes, this is something known as competing risks, right? Our bad outcomes are sort of competing for our attention, so to speak. Okay, it's pretty common in contexts like transplantation where there are lots of different things that can go a little bit wrong. Actually, maybe that's true of all of life. Lots of things can go a little bit wrong. So we want to try to avoid all of these things, but they might have different mechanisms. We can't necessarily treat them as, a basket of bad things. We might actually need to see how our choices, in this case, to give or not give a kidney from a Hep C positive donor could affect these different bad possibilities. Now, the research into this personalized or precision medicine in the context of competing risks has been pretty limited. So there's been some work looking at what are known as cumulative incidence functions, which have phenomenal statistical validity and very, very little interpretability. So those exist, but I think are not terribly helpful for actual clinical deployment. And so that was sort of a clear gap that my student Misha sought to fill, is to find some easily implementable methods that yield interpretable treatment rules. All right, so what we did is we adapted an adaptation of something else. And the reason I'm telling you about the thing that we started with, which is something called dynamic weighted ordinary least squares, is because it's really simple. So I'm going to explain the really simple thing, and then I'll tell you about the sort of ways we elaborated it for this particular case. Because this DWALS, the sort of base method that we used, it's just a weighted regression. So if you know more or less what regression is, then you're going to understand everything I'm talking about, because everything will build on that. Okay, so it's weighting where weights can address for imbalances due to confounding. So for example, the characteristics of patients who accept a kidney from an HCV positive donor may be different from the patients who do not. Okay, maybe healthier patients are willing to wait a little longer for an HCV negative donation, for example. Okay. This method is something called double robustness. What that means is I don't have to correctly specify all my models. I'm allowed to make a few statistical errors in my modeling decisions, and I can still get the right answer. So that's what double robustness is about. I'm going to model two parts of my data features. I only need to get one right to get the right answer. And it's pretty straightforward method. So what we're going to do, and I'll show you a little more detail about this method, is this idea of weighted regression to try to find those treatment covariate interactions so we can see those thresholds of where you do or don't want to offer a given treatment option. What we do from that is extended to a survival setting through something called a weighted accelerated failure time model. Accelerated failure time models is sort of the other big class of survival modeling. Everyone's heard of Cox modeling? Yeah. AFT is the other one. It's less used. It's so great. The reason it's so great is that you actually model the survival times. So if we think about sort of interpretability, we can talk about how much longer a patient would survive or how much longer they would live with a functioning graft before graft failure. So we're actually modeling on the scale of the thing we care about rather than on hazards. Okay. All right, so this idea of regression-based approaches to learning about precision medicine is we're really just trying to model the expected outcome. So if we think about my cartoons, that's what I'm doing. I'm trying to model that outcome, like my quality of life, or in this case, my time to graft rejection or time to death. I'm trying to model that as a function of my patient covariates as well as my treatment, where in this case, by treatment, I really mean a kidney that is from an Hep C positive or Hep C negative donor. Okay? So I'm going to model my expected outcome as a function of my treatment of interest, these covariates and potential interactions between them. I'm going to take care of confounding through that direct modeling of the outcome, but I'm also going to use some weighting to have that robustness property so that if I get my outcome model a little wrong, I can rely on a propensity score to try to take care of those imbalances. Okay, I'm going to estimate my regression parameters so that I can learn about where those lines cross and use that to tell me how to allocate treatment. This is as bad as it gets, more or less. Okay, what we are modeling, I know that online you can't see when I point at things. So on the left side of the equal sign, that's just my expected outcome. Okay, my quality of life, or in the case that I'll be talking about today, my time to a bad thing. Okay, time to graft failure, time to death. On the right-hand side, I've got my covariates and my treatment, and I've just split them up into two pieces. What's in red, the impact of the treatment. So this is anything involving my Hep C positive kidney. So Hep C positive kidney or not, interaction of that variable with any covariates. Okay, that's what's in red. That G of X function is everything else. Okay, the impact of sex, the impact of age, the impact of, I don't know, shoe size. I mean, you name it. Whatever goes into that model, that goes into that G of X function, and I don't really care about it. It's there to help me model my outcome. It's there to adjust for confounding. It doesn't tell me anything about treatment. Okay. So we just focus on the part of my regression model that includes the treatment. So that's really what I care about. And why do I care about it? Because I'm assuming that the patient characteristics, those X's, age, sex, treatment score, Karnofsky score, you name it, those things come fixed with the patient. The one thing that I can change is whether or not they get a Hep C positive or Hep C negative kidney. So that's the thing that I'm considering manipulable. And so if I focus on giving one or the other, I can see whether that raises or lowers my outcome, right? The X I consider fixed. Those patients come to me as they are. I can see the impact on their outcome of what treatment I give them. So I'm going to model this, and then I'm going to look at predictions of the outcome under my competing treatment options and see which one is better for any given patient profile. That's the idea behind this. Okay, so again, what I'm trying to do is identify plots like the one on the far right. So I'm trying to identify covariates that interact with my treatment or my exposure of interest. And how I typically do that is with equations like this one on the second to last line. Can I see if I'm pointing at the screen? Okay. Excuse me. So essentially what I'm doing is I've got a main effect of treatment. I've got my treatment A times a covariate, times a parameter, and then I've got interactions of the treatment with other covariates. So it's a linear regression model with interactions. That's kind of as complicated as it gets. Okay. What I want to do is make my outcome bigger. Right? I've taken Y so that Y is coded that bigger is better. So I live longer, I have better quality of life. If you want to minimize the outcome, the methodology is essentially the same, or you can stick a negative in front of it. So minimizing or maximizing doesn't actually change the general method. But if I want to maximize this outcome and I have a treatment that's coded 0, 1, well, anytime what's in the is positive, it's better to give treatment A equals 1. If it's negative, it's better to give treatment 0. That wipes this out. That's how I'm viewing this, that I've got this function of covariates. The covariates don't change. The patient characteristics don't change. I just get to manipulate what treatment a patient gives to see the impact of that on their outcome. So how I actually do that is I set up a model for the outcome and a propensity score, as I mentioned. That's just something we use to address confounding. I use the propensity score to create a weight, and I fit a weighted regression. Okay, that's all you need to know. If you can fit regression, you can do this. Okay, you don't even include propensity score, you can still do this. You lose that robustness, but you can learn about these adaptive or these personalized treatment strategies just through regression by looking for these treatment covariate interactions. So if there's anything I want you to take away from this, it's that it's not conceptually difficult to learn about how to tailor treatment. Okay. Data-wise, it can be difficult. Treatment covariate interactions are often very poorly powered. We do need large data sets, but conceptually, we're just looking for this type of figure. Okay. We've got lots of different weights that will satisfy the assumptions we need for balance. As I said, the worst equations will be in footnotes from now on. But basically, we're going to fit a weighted regression and look for those crossing lines. So what I like about this method, I like that it's regression-based. Why? Because I think it's way easier to explain to people who don't necessarily want to look at big black box stuff, right? It's easy to explain what I'm doing when I'm looking for these crossing lines. The other thing that's really nice is the sorts of treatment rules we get out of this look like this bottom line here, right? It's basically a score. It's like a Framingham risk score, right? I've got loading values psi that I attach to covariates. I sum up this score and I see whether it's bigger or smaller than a given threshold. So with a relatively small number of covariates, you could literally do this on a napkin, right? We just have these estimated loading factors for how much a given factor influences whether or not a patient should receive one treatment or another. So it's easy to see how covariates are affecting our treatment decision. There's not a black box element to it. It's easy to interpret whether there's face validity to our treatment rules because you can see whether a given treatment or a given covariate is increasing or decreasing the need for a particular treatment. All right, so I guess the main limitation is exactly that, though. These are linear decision rules. So we add a certain weight to covariates, then we sum them all up. If we need something more complex than that, if we need a tree-based rule with either or type decisions, this method doesn't work very well. All right, that was the regression setting with just a regular continuous outcome. If we move into a survival setting, we have to worry about censoring. So not actually seeing the survival times for everybody, but having some truncated survival times. So we do that by moving that weighted regression into this accelerated failure time model. Yes, question.
You offered that we interrupt to make sure we not just nod our heads. So one thing that I want to make sure that I understand. So in the process of considering the variety of potential covariates,
Yes,
as contributors to the weighting mechanism, there isn't some kind of a process of selection or to say which should be included in the weighting, which not. I think this was the last point that you were making before.
Right.
So all of the variables that you might want to include are going to be there, even if they're correlated or not. Or is there some kind of selection process that takes place in the background?
There absolutely can be. In the example I will talk about today, we did not do any selection because we had relatively few covariates compared to our 300,000 patients. But we absolutely can do selection either in the propensity score or in the main outcome model. Usually we do it through a penalized approach, something like lasso. I don't know if that's familiar. But there are different ways of doing it, but the penalization approach of sort of shrinking out things that don't seem important is the way we typically do it if we are worried about having too many covariates. We don't worry about correlation, but yeah, if we have too many, then we do try to shrink them out just to also to simplify the decision rules that we have.
So it's mostly basically, let's say, a statistical process rather than content related decision making.
I'll take
or
that
a combination.
For sure. Nothing goes into the model unless a clinical collaborator tells me it should. But things might come out of the model based on statistical evidence that it doesn't belong in there. So I guess my starting point would always be talking to the collaborators to make sure that we aren't overlooking anything. And sometimes, if someone tells me there's an important factor that they want in the model, I don't allow penalization of those factors. So we can certainly force things in. We could, I suppose, force things out, but I wouldn't necessarily unless I needed to. Thanks. Okay, so we had our regression approach. We then moved it into a survival approach where the survival approach focuses on modeling not hazards, but the actual time to the event of interest. How we do that is fairly straightforward. We model the log of the survival time. Just for those of you who are familiar with log transforms, they make things nicer, right? They take big, long, skewed distributions and make them a little bit more symmetric. And we handle the censoring through weighting. So we end up with a longer footnote. It's essentially the same procedure of a weighted regression where we're modeling the log survival time rather than an untransformed outcome with a weight that now accounts for both a propensity score and a probability of being censored. Okay. So the basic ideas are the same, but we're addressing imbalances both in the sort of selection of whose outcomes we get to see versus who gets censored, as well as confounding due to potentially different treatment allocations to different covariates. All right, so it was pretty simple to step from uncensored to censored data. Okay. Again, it's really easy to implement this because we're working in a regression context. Once you log transform the outcomes, you can still use linear regression. So it's almost exactly the same code as you would do for the D-walls, just the extra step of adding in the censoring weights. The assumption we make is not quite the same assumption that's usually made in Cox survival modeling of independent censoring. We're actually assuming something a little bit weaker, which is that the censoring is independent once we account for the confounders or the covariates that we include in our censoring model. Okay. And so now what Misha has done is taken this idea and extended it to an idea where we have multiple outcomes. So lots of bad things that can happen, or in this case, 2 bad things that can happen, and also accounting for the clustering across the 250, transplant centers. All right, so the idea is that this doesn't count as an equation. I told you we're done with equations. The idea is that we are looking for a treatment that optimizes some outcome. In this case, what we're trying to optimize is the time to something bad happening. Okay. Now, in an ideal world, I know what bad thing is going to happen to what patient. So I can say, Erica, your graft will fail. I'm going to focus on maximizing the time to graft failure for you. Phil, I'm picking on you. I'm sorry. Phil's graft is not going to fail. Phil will eventually die. I'm sorry. They're my only 2 outcomes. Because I know this, I'm going to focus on making you live as long as possible. And I don't worry about graft failure for you. Of course, I'll die eventually, but the graft failure is coming for me first. So we'll focus on my graft failure. But that, of course, requires omniscience. It requires you to know that my graft is going to fail and Phil's isn't. Right? So in an ideal world, I would know that bad thing that's coming for each patient and try to optimize that. But of course I don't, right? And that's the real challenge to trying to apply these methods in a setting where there are many bad things that can happen. So there's different ways that we could try to tackle this problem. Okay, one way that we could do this is say, well, I don't know what bad thing is going to happen. So what I'm going to do is make a guess at what is the most likely thing to happen. Okay, and so maybe I guess that both Phil and I are likely to have graft failures. Okay, and so I'm going to treat both of us in a way that maximizes our time to graft failure. And I get lucky because we guessed right, and Phil is unlucky because we guessed wrong. Right, so that's one approach. This in the sort of computer sciences literature would be known as a greedy approach. I'm going to target the most likely thing. Another approach is to say, I'm going to hedge my bets. We could all have graft failure. We could all die. We don't know which is which, so I'm going to weight by the probability of each one of those things. If the chance of my graft failure is really high, then these two strategies would probably be pretty similar because I'm going to be giving a lot of weight to the graft failure. But if we're kind of 50-50, then I'm really hedging my bets and giving equal weight to the probability of dying or the probability of graft failure and treating you according to that uncertainty. Okay, so this is sort of a weighted average approach or a greedy approach of targeting what I think is the most likely cause for a given person. Not surprisingly, what's better really depends on the situation. Okay. How similar are the rules? So if the best treatment for avoiding graft failure is pretty similar to the best treatment rule for avoiding death, then it doesn't really matter which one you pick. But if one treatment were to prolong the risk of one thing but shorten the risk of another, then it matters a whole lot which of these rules we choose. It's out, though, that the differences between these two is really small compared to the difference of ignoring the fact that you have multiple bad outcomes. All right. Oh, I did lie. I lied and lied and lied about how many equations I had. I'm incorrigible. I love my stats. All right. What are we doing, though? These don't count. We'll pretend these don't count. I'm modeling my expected time to a bad thing. Okay, that's what that first equation says. It's just an expected time to a graft failure, expected time to death. Okay, my weighted optimal rule is just going to look at those treatment covariate interactions weighted by how likely I think it is that each event will happen. So I've got a separate model for each outcome. I'm going to weight those probabilities and try to lengthen the time, that weighted time, to those different bad outcomes. My optimal greedy rule is the opposite of that. Really, I'm going to try to take a good guess at what the outcome is and then maximize the time to that. So that contrast function, the part of my expected outcome that involves my treatment of interest, that's the real key, right? That's the thing that's telling me how to adapt my treatment. And we can use that to describe how much better one treatment is compared to another. That's really, oh, I hate when people flip back, but I am going to do this maybe. No, I'm going to stop flipping back. If we think about my cartoons, right, where I had the two lines crossing, the benefit function, okay, this benefit that I'm talking about here, that's just the distance between the two lines. Okay, so when the distance is small, it doesn't matter much which treatment decision I take. The bigger the distance between the two lines, the bigger the benefit. And of course, it's covariate specific. Where I am on that x-axis determines how big that benefit is. All right, so we did a whole ton of simulations just to get a sense of what these are. And the things we looked at were things like the benefit of the ITR. So how much better do I do under an individualized treatment rule compared to a rule that always assigns treatment by a flip of a coin, for example, or always assigns a specific treatment. We also looked at the success of our estimation in terms of assigning treatment, because in a simulation, you know, I know the truth. I know the underlying truth, so I can compare my estimated treatment to what would be the optimal treatment. And we could also see the impact of giving my estimated rule as compared to giving the truly optimal rule. So the first thing I'll show you, these plots are just showing that double robustness property I mentioned. So on the far right of each of my panels, it's assuming I know everything and I modeled everything correctly. The two middle ones are showing what happens if I misspecify one of the rules. or one of the models, and then the far right shows what happens if I misspecify both. And we can see on the two panels on the left, sometimes misspecifying both can be dramatically bad. In the two panels on the right, we see it isn't always dramatically bad. Sometimes you get lucky. But if you misspecify just one thing, you still do very well. Okay, so that's reassuring. I need to know what covariates to put into my model. I don't necessarily need to know the functional form. I don't need to put a spline or be super flexible. I can still be kind of wrong and do well in terms of estimating the parameters. So those parameters are the things that make those loading factors on my treatment decision rule. What I'm showing you here are those benefit functions, okay? The benefit functions on the left-hand panel are from the weighted rule and from the greedy rule on the right. And it does exactly what you might think. So if we start with the greedy rule on the right, you can see exactly what happens when I'm predicting the treatment correct, or sorry, the cause of failure correctly. So in both of these on the far right of the right-hand panels, the red, which is the truth, agrees perfectly with my estimate. These are the patients for whom I predicted the outcome right. Okay? Erica's going to have a graft failure, and I predicted she would. So the benefit of my prescribed treatment is exactly what it should be. But it's bad for the people for whom I've guessed wrong. Over here on the left-hand panel, we never see that perfect agreement because everywhere we go, we're hedging our bets. Okay, so I'm always a little bit wrong, depending on how much weight I'm giving to the thing they actually experienced versus the alternative. Now, which one of these is better? It's better if I guessed right for you. But depending on the setting, sometimes this is just one of the examples we looked at. Sometimes the weighted rule, it's never exactly right, but it's actually much closer everywhere. Whereas the greedy rule will always be exactly right for some people, but can be substantially wrong for others. All right, what I want to show you here, it's a lot of numbers, but there's just patterns I want you to focus on. We did lots and lots of simulations. That's what's in the different columns. So the first thing I want to focus on are the top two rows, which is the difference between the proportion optimally treated under the weighty rule versus the greedy rule. And within every setting, they're about the same. It's not always 3/4, right? We can see sometimes it's 90. What's more relevant is the fact that the weighted and the greedy are basically similar to one another. Okay, so whether I take this hedge my bets approach or my greedy approach, it doesn't really matter to how successful I am in estimating the optimal treatment. The next set of, the next pair that I want to look at are these V's. This is the expected outcome, the survival time under the weighted and the greedy rule. And again, each pair of these is roughly the same. So I'm generally allocating the right treatment in the same proportion, whether I take the weighted or the greedy approach, and generally the effect on the patient's survival time is the same. If we compare these to the bottom two rows, so DO, that's the oracle. That's the truth, giving people the treatment they actually should be getting. You can see that obviously this is better than any of our estimates, but it's not so much better. The uniform is flipping a coin. Okay, that is certainly worse. We can also do this by withholding treatment from everyone or giving treatment to everyone. So giving them a fixed treatment strategy rather than one that personalizes. That's also not much better than the uniform. Okay, so what we're seeing is that greedy and weighted are similar to one another, a little bit worse than knowing everything, which is not so bad, right? We'll never know everything, but if we can be not too far off by estimating, that's good. The final thing I want to show you is this column here, column 10, or simulation setting 10. In this one, we also looked at a single cause-specific analysis. So picking one of the two causes and ignoring the other. because that's one of the approaches that people have taken in this multiple outcome setting, is saying, well, I'm just going to focus on death, forget graft rejection, for example. That's the worst outcome. I'll focus just on maximizing time to death. If we do that, we do so much worse by ignoring the fact that there is actually another bad thing that could happen to patients. So ignoring one of the competing risks is definitely not the way to go. Another approach that could be taken would be to compute a composite outcome. So say any bad thing, graft or death. In many of these, that performs similarly to the weighted approach, because effectively you're sort of weighting in an unprincipled way, right? We're not actually weighting by the probability of any patient having a particular outcome, but just saying we're going to give them equal weight.
The issue of the relationship, sorry. There's the issue of the relationships of the covariates with the outcomes that may be in a similar direction versus not, right? So
absolutely. So if the covariates, so in this case, for example, if the covariates act in the same way or in a similar way for both death and graft, then it doesn't matter much what you do. If they act in different ways so that they increase one bad outcome and decrease another, or the treatment covariates do, even if the sort of main effects don't, then you can see more dramatic differences between the two for sure. Okay. Oh, I've got to keep an eye on my time, but we're almost through the fun stuff. So just going back to our kidney transplant, got those 300,000 patients from 251 centers, roughly 16% experienced the first cause, graft failure, and the other 16% died. In this particular database, 3.6% of transplants were from HC positive kidney donors. Among those recipients, among the HCV positive recipients, almost a third received from an HCV positive donor. So you can already see that there's some differences between who's getting the HCV positive kidneys and who isn't. There's clearly imbalances in our patient population. So we wanted to see which tailoring variables would suggest a lower risk for receiving a kidney from an HCV positive donor. So it's seen as a negative thing. Is it negative for everyone? Can we minimize risk by giving it to patients who are less likely to be harmed by it? Okay, trying to maximize the time to either of these bad things. As I said, we didn't have a whole lot of variables available to us, so we put them all in and did no selection because we weren't worried about power given our large sample size. So we had the patient or the recipient HCV status, the donor type, whether they were living or dead, donor age, and other potential confounders. So sex, ethnicity, comorbidities, smoking status, and size of the transplant center as well. Okay, if we look at the coefficients associated with having an HCV positive donor, and again, this is where I find the regression-based approaches are helpful because we can look at these and see if they passes the sniff test. Right? What do we see? Well, getting an HCV positive or a kidney from an HCV positive donor is bad. It's got a negative associated with it. But if the recipient has HCV, it pretty much wipes it out, right? The risk is the HCV. There's nothing else risky about that kidney. So if the receiving the kidney already has HCV, there's really no harm at all in receiving an HCV positive donation, either for graft failure or for death. We can see that maybe there's still a little bit of risk associated with receiving an HCV positive kidney for death, but not much. There's no effect whatsoever of the age of the donor. Donation type, again, living donors tend to have more successful outcomes for the patients. So what do we see from this? Well, certainly we can see if a patient has HCV, it's a reasonable thing to consider giving them an HCV positive kidney. But also, if we've got a living donor, outcomes tend to be pretty good. So maybe it's worth taking a donation from a live but HCV positive donor rather than standing or sitting, waiting, lying on the waiting list. All right, so our treatment parameters were pretty similar across the two causes, which goes back to what Ruth was saying, that if the rules are similar for the different causes, then it doesn't really matter whether you take a greedier approach or a weighted approach, or even just target one, because in this case, targeting one is quite similar to targeting the other. What we found in this analysis, though, is that a substantial number of patients, because we have a lot of living donors, could benefit or at least not be harmed by taking an HCV positive kidney. So 28%, 20%, depending on whether we look at the greedy or the weighted rule. That's a lot higher than the 3.5% of patients we saw receiving the HCV positive kidneys. So if you believe my analysis, and I'm not saying you should, I'm a statistician and I'm having fun with this, but I don't know that this is clinically ready for deployment. But at least this analysis suggests that up to a fifth of patients should not decline a kidney simply because it's from an HCV positive donor. Okay. What else did I want to show you? In the interest of time, I'll skip this. These are just the benefit plots. I think what I'd like to finish off with and leave a bit of time for questions is, this method that I've deployed has really always focused on better treatments. Which treatment is better for what person? And we've sort of flipped that here and said, well, which treatment is not harmful for a given person? And this can be a really important question to ask. If we're often in a question or in a situation of constrained resources, kidneys don't grow on trees, right? They grow inside of us and not everyone wants to give them up. So we have constrained resources either through physical reasons like kidneys, financial reasons. So sometimes we need to think about giving potentially suboptimal treatments in a way that does the least amount of harm. But we need to be super careful in doing this, because when we are deciding whether there is harm or not, I will go back to that benefit plot for a minute. What we're really looking for is cases where the benefit doesn't appear to be different from zero. We're trying to avoid harm. But if you remember back to something like Epi 607, right, there is a difference between rejecting and failing to reject the null hypothesis, right? We are saying for some people, it is definitely harmful to receive an HCV positive kidney. For others, we have no evidence that it is harmful, but that doesn't mean we're certain it's okay. Right? We might be in a situation of low power. So we have to be a little bit careful about how we're doing these tests to make sure that we're not saying, it's okay, just because we don't have enough data or enough evidence to conclude otherwise. The other thing to be wary of in this analysis in particular is there's so much I don't know, right? Kidneys are not sitting around waiting for you to make a choice between HCV positive and negative. They come up, they're in a region, it's a much more dynamic thing. There is a priority list. We weren't able to account for that. We did not have any information on geographic proximity, where people were in the waiting list, and so on. So we don't actually know to what extent this would be possible to deploy. As I said, it's not like a patient asks for a kidney and there's a smorgasbord waiting for them to choose which one is least or most harmful. So there is still a lot that we certainly couldn't account for that makes this a fun statistical exercise, but not really a clinical decision-making exercise at this point. So I think I'll stop there. Yes, I will stop there. Thank you.
So great talk. Thank you very much. I think well for this audience. So I have a question, and it reflects my naivety, I think, about the methods in general, but the optimal treatment methodologic advance that you presented was built upon sort of a doubly robust modeling the treatment and modeling the outcome.
Yes. And in
Could
this
it be-
case, censoring as well.
And censoring,
Yeah.
Could it also have been done sort of without the outcome modeling and just modeling the treatment and modeling the censoring, sort of an IPW MSM, take those gammas or betas or whatever the score, the loading factors are, and plugged into the optimization, or it really requires that doubly robust piece?
So this particular approach really does require the doubly robust piece, but there's a whole group of precision medicine methods or, statistical methods that are just IPW approached. I don't love them. The main reason I don't love them is because IPW alone is super variable. It tends to lead to really big estimates. And because we're looking for these treatment covariate interactions, which are already hard to detect, anything that loses me power makes me unhappy. But there are doubly robust versions of IPW. So there's the augmented IPW class, which can be used. Then that does put you again into having to model those outcomes, though. So
I'll just have to learn it then, because I've been sort of my way forward. Any other questions?
Great talk.
Even though I said you died and I only get graph failure?
No, I'm an easy audience member. Regarding inference, this is maybe like into the weeds a little bit, but you show double robustness. So like that implies consistency if you misspecify,
Yep.
one of your nuisance parameter estimators. Do you still get valid confidence intervals when you misspecify one? Okay.
We do, but actually in the single, so I've only presented one decision rule here. Like we're not doing the multi-stage decision making. So in the single stage, it's very straightforward. We have analytic expressions that basically do the delta method to account for the estimation of the propensity score and the estimation of the censoring models, but we bootstrap everything.
Gotcha. Okay.
And actually in this case, I didn't show you. Oh, I didn't. I knew I took out at least some of my equations. We actually embedded all of this in GE on top of that to account for the clustering within centers. So for this particular example, we did we resampled the centers in terms of our bootstrapping. So we resampled centers, then we resampled individuals, then we refit all of our nuisance models. So it was sort of like this massive bootstrapping operation, but it is possible to do delta methods as well. You do get much bigger confidence intervals. If misspecifying the treatment model is not so bad, misspecifying the outcome really inflates the variance.
Right. That makes a lot of sense. And so it's like compared to like the CIs that you have here, like when you tried actually using the delta method, did you see a big difference between the bootstrap and the delta method, or
no, it's more just it's a hassle.
Yeah,
it's a massive hassle, but we don't actually see huge differences between the bootstrap and the two, at least in these like relatively large data settings.
Very cool. Yeah, and it makes it much easier to apply, like explain, I think, than go through the theory. Cool. Thank you very much.
Are there any questions on that? Sorry.
Thank you for a great talk. This is a layman's question. I'm thinking about who actually decides what's optimal, and I'm asking policies that guide this in terms of, or is that left to the discretion of the clinicians and maybe statisticians?
I might have to turn to Ruth for this. I mean, I know there are priority lists for trans. Nobody consults me when a kidney comes up. So I think the statisticians are often left out of the loop, but I don't actually know the details of that.
Well, the organ allocation, at least in Quebec, there's a scheme where in a context where two organs, one of them being life-saving, in addition to the kidney, so heart or lung might need to be allocated. There's priority in allocation there. Children get priority, for example, but then for the kidney, most of the waiting list is composed of patients waiting primarily for kidney alone. And there's some, not just priority, but there are some restrictions in the allocation that we're doing. But those restrictions, to a certain extent, are already taken into consideration in
get
your
into the-
model by
okay.
virtue of those covariates, right? Patient-related covariants.
Right.
So I would love, I must say, I'm really excited, but by what you're showing, and I would love to learn more, frankly, about the nitty-gritty of
Yeah.
this and what variables are going into this and so on. So I'll stop there and let
Okay.
you continue.
I mean, we've done, I don't want to say similar work, but I've done some work with clinician at, well, she's at the University of Washington now it was a transplant context, but a different one. We were looking at stem cell transplantation for leukemias and looking at which immunosuppressant therapies to give, like whether to give the sort of really strong, kind of a non-specific, highly T lymphodepleting ones versus more standard ones. Because the sort of stronger ones, they reduce the risk of graft versus host disease, but they also come with greater immunosuppression, so patients can get all sorts of other opportunistic infections. And again, it was kind of interesting seeing what factors would come up in terms of the allocation. So that was very different because everyone was getting the transplant. We weren't deciding who or what, but rather how to treat them before the transplant. And if they got graft versus host disease, what immunosuppressants to give them. And we saw really interesting factors like how, what what's the word? The grade of the cancer that they were getting the transplant for was a big factor. The HLA match, the closeness of the match of the donor to the recipient was also a big factor in how strong the immunosuppressant should be. So again, the things that we saw coming up really agreed with what we expected, even in my very, layperson's understanding of the biology, it seemed to be agreeing with what we expected and giving rules that made clinical sense from what my collaborators were telling me. But again, I don't know that our data quality is enough to really use any of this work to change guidelines, but maybe to inform clinician thinking. Does that make sense? Like it's not, I wouldn't feel comfortable deploying this given the many subtleties in the data that we weren't able to account for.
Just a point apropos the clinical context. So just touching on the point of living donors with HCV versus deceased donors. So if this is a question of allocation, there's obviously oftentimes it's a deceased donor list.
Mhm.
So there isn't in most patients the option of making, of being offered a living donor in that context,
Right.
right? So I would remove the living donor
Mhm.
data out of this decision making because
Okay.
there the contrast has to be living donor with HCV versus living donor without HCV rather
Right.
than living versus deceased donor, right?
Yeah.
Unless this is the clinical question to be answered, a living donor with hepatitis C versus a
Mhm.
deceased donor
Without.
right?
Yeah.
Because inevitably, living donor transplants offer better graft and patient survival.
Right.
Okay.
Are there any questions online? No? Okay. Well, thank you so much, Professor Moodie. It was wonderful. Thank you.